Hello and welcome to Science for Sleep. I'm really glad you've drifted into this little corner tonight. Maybe you're already stretched out under something warm and familiar, or maybe you've simply carved out a few quiet minutes between the busy pieces of your day. Your room might be nearly dark, or softly glowing, or lit just enough that you can still make out the gentle outlines of the furniture around you. Maybe there's a window cracked open, letting in a bit of cool night air. Wherever you are, whatever your setup, this space is yours now. A small refuge where you don't have to be anywhere else or anything more than exactly who you are. A pocket of stillness where science can loosen its collar, settle down beside you, and wander at an unhurried pace. This isn't a lesson. It's not a lecture hall. There's nothing to study, no pop quiz hiding around the corner, just ideas moving slowly enough for you to relax into them. You don't need to remember everything. You can let your mind drift, fade in and out, even fall asleep halfway through and wake up with only a hazy impression. That still counts. That is the experience, because some of the most interesting thoughts arrive quietly slipping in when we're too comfortable to interrogate them, too relaxed to chase them away. Tonight, I want to explore something that has puzzled scientists, mathematicians, philosophers, and honestly any curious child staring up at the night sky for centuries, the idea that the universe might be infinite, and yet somehow might also have an edge. At first glance, those two ideas feel like opposites that shouldn't be allowed in the same sentence. If something goes on forever, how can it possibly have a boundary? Doesn't infinite mean endless, no walls, no borders, no final stop? It feels like one of those questions that is either too big to ask or too simple to articulate. And yet here we are leaning into it anyway, because this is what humans do, especially at night, when the world finally quiets down and our minds wander toward the bigger, stranger questions. So let's sit with it together. Let's turn it over gently and look at it from different angles, not to force a definitive answer, but to understand what we're even talking about when we use words like infinite boundary or even universe. Sometimes understanding the shape of the question is more meaningful than the answer itself. But before we float too far into cosmic mysteries, let me ask you something small and simple. What time is it where you are right now? Not because I need the information, but because it's a soft reminder that we're not only moving through space, we're moving through time too. You're living inside a moment, a tiny, irreplaceable flicker in the enormous stretch of what was and what will be. And while you're here with me, this moment belongs only to you. Somewhere far beyond your room, galaxies are spinning, stars are being born, comets are gliding through cold darkness. But this minute, this pause in your evening, this breath, this one is yours alone. There's something quietly beautiful about that, this moment you're in right now. If you're already sinking into relaxation, feeling a little curious or drifting somewhere between wakefulness and sleep, I'd truly appreciate it if you tapped the like button. And if soft science flavored stories are something you want to keep within reach, you're welcome to subscribe as well. I always love hearing where people are listening from a small seaside town, a buzzing city apartment, a tucked away cabin beneath tall trees, or simply a warm bedroom with a soft blanket and a dim evening lamp. If you feel comfortable sharing that in the comments, it's like watching a constellation of listeners slowly light up across the globe. It makes the universe feel just a little more connected. And just a gentle reminder, this video is here for calm curiosity and comfort. It's not medical advice, and it won't cure insomnia or anxiety on its own. But maybe it can give your mind something soft to rest on, something to wander through while your body unwinds. That's my hope anyway. So let's ease into things. No rush, no pressure, just ideas drifting at their own pace. Maybe you're lying back, eyes on the ceiling, or eyelids growing heavier, feeling the weight of the bed holding you like a quiet anchor. And maybe at some point in your life, maybe tonight you've wondered what lies beyond everything you can see, not just beyond your bedroom walls or the edge of your neighborhood, but the real beyond, the one above the clouds, past the planets farther than any telescope can quite reach. Maybe you've heard the phrase the edge of the universe and imagined it literally like the edge of an ancient map where the stars taper off and there's nothing but blankness. Or maybe you picture a sleek spaceship flying straight towards some kind of cosmic border only to stop at a glowing wall, unsure whether to turn around or push through. But then someone says, the universe is infinite, and that whole idea dissolves. If it's infinite, then there can't be an edge, right? Nothing ends, nothing stops, it just keeps stretching out forever. And yet, infinity is its own strange thing. It's not something we ever see directly. We can imagine huge numbers bigger than all the grains of sand on every coast, bigger than all the stars in our galaxy. But infinity isn't a huge number. It's a concept, a direction with no finish line, a road where you never see a final exit sign. So, how can both ideas, infinity and an edge, exist in the same breath? The truth is, no one has a complete answer. Not yet. But we have ways of thinking about it, ways of modeling the possibilities, ways of exploring what the question even means. Some approaches come from mathematics, tracing shapes and geometries too large to imagine. Others come from philosophy, asking what it means for something to end at all. And many ideas come from astronomy, from real measurements taken by telescopes, satellites, and observatories peering deeper into the cosmos every year. Some of these ideas have been tested, some are still being shaped, but they all orbit the same enduring mystery. What is the universe actually shaped like? And if we could understand that shape, what would it tell us about whether the universe has an edge or doesn't? And when we ask about the edge of the universe, we need to be careful with what we're asking. Are we talking about the farthest place you could travel if you kept going in a straight line? Or are we asking about the edge of time, the beginning of everything, or the point where everything might one day end? Or maybe the question we're asking is even more fundamental. Is there a point where space simply ends? A boundary, a limit, a place beyond which there is no more space to move into? That's the topic we'll explore tonight, step by step, in a calm, systematic way. We'll look at the geometry of space. We'll discuss how curvature works on a cosmic scale. We'll examine the expansion of the universe, the meaning of an observable horizon, and how our position as short lived observers shapes the kinds of questions we're able to ask. We'll also consider what it means to travel in a straight line forever. If you could move without stopping, without aging, without turning, what would happen? Would you eventually hit a physical edge? Would you loop back to where you started? Or would you continue indefinitely without encountering any boundary at all? We'll move through these ideas slowly. Infinity is not something that needs to be grasped quickly. Understanding large scale structure requires patience, the same kind of patience built into the universe itself. So, wherever you are right now, let your thoughts settle a bit. You don't need to clear your mind. Let any remaining distractions fade into the background while we focus on a single, large question. Let's begin with a simple model. Start by imagining an ordinary room. It has walls, a ceiling, a floor. This is a closed space. Its limits are obvious. If you walk to the edge, you reach a boundary. There is no confusion about where the room ends. Now remove the walls. Remove the ceiling. All that remains is a flat floor stretching uniformly in every direction. You begin walking in a straight line. There are no objects, no corners, no barriers, just the same flat surface, continuing without interruption. You don't get tired. Time doesn't matter for this thought experiment. You simply keep moving forward. Eventually, a question arises. Will you ever encounter anything? Will you fall off the edge? Will you find a border? Or does the surface extend infinitely? And consider another possibility. What if after an extremely long time, you return to your starting point without ever turning around? What would that imply? It would suggest that the surface isn't truly infinite. It's curved in a way that allows straight line motion to loop around. In mathematics, this is a property of certain curved spaces. It means you might be moving on the surface of a higher dimensional structure without realizing it. Now scale this idea up. Replace the floor with the fabric of the universe itself. Replace your walking with the movement of galaxies or with the path followed by light. Then ask the same questions. What is the geometry of space? Is it flat? Is it curved like a sphere? Is it negatively curved like a saddle? Is it open-closed or something more complex, possibly involving higher dimensions? These are active questions in cosmology. Tonight, we're not looking for a final answer. We're exploring how scientists approach the problem, what models they use, what measurements they rely on, and how these models try to explain whether the universe has an edge or is unbounded. Before we move forward, consider one final idea: the shape of stillness. It sounds abstract, but scientifically, stillness simply means the absence of motion relative to something else. Even without visible movement, space itself can still have structure. It can be flat, curved, expanding, or static. Stillness doesn't eliminate shape. It just means the shape isn't changing in a way we notice. When most people imagine space, they often assume it's flat. Not flat like a tabletop, but flat in the geometric sense where straight lines remain straight, parallel lines never meet, and the rules you learned in basic geometry still apply. On a flat surface, for example, the angles of a triangle always add up to 180 degrees. And if you travel in a perfectly straight line, you never curve back toward your starting point. That's what flat space means. Distances behave intuitively, and shapes follow predictable rules. However, on the scale of the entire universe, space doesn't necessarily follow these familiar patterns. When you begin asking questions about the cosmos as a whole, the geometry becomes more complex. Picture again that infinite featureless landscape. You walk forward in a perfectly straight line, never turning, never deviating. If space is truly flat and infinite, you will keep encountering new regions forever. You'll never return to your starting point because the space doesn't curve back on itself. But if space has curvature, even a very slight amount, something unexpected can happen. You could continue walking straight and eventually arrive back at the place you began, not because you turned around, but because the structure of space itself bends your path. In that case, space has a shape, not one you can see from inside, but one that determines how movement works. It might not have a center, it might not have a physical edge, but it still has geometry rules that govern how lines extend, how paths evolve over time, and how motion unfolds. A common analogy is the surface of a sphere. Think of the surface of a balloon. From your perspective on that surface, everything appears flat. You can choose any direction and walk in a straight path. But if you keep going long enough, you eventually loop back to your starting point. There's no boundary, but the total area is limited. You never encounter a wall, yet the space is finite. Still, that analogy is only a simplified model. The universe is not a two-dimensional surface embedded in a three-dimensional environment. As far as we can tell, it has three spatial dimensions: forward, backward, left, right, up, down. If the universe is curved, that curvature would occur in a higher dimensional sense that we cannot visualize directly. This is where human intuition becomes unreliable. We can express these shapes mathematically using equations from general relativity. We can simulate them on computers or represent them using graphs. But we can't mentally picture the actual geometry the way we can picture a sphere, a map, or a flat sheet of paper. Even so, the geometry exists. It influences how galaxies move away from each other, how gravity bends the path of light, and how the earliest fluctuations after the Big Bang spread throughout the cosmos. In that sense, the shape of space is the structural backdrop for every form of motion in the universe. We rarely think about this backdrop because our attention is usually on the objects inside it: stars, planets, clusters of galaxies, and the overall expansion. But just as the surface of a lake controls the behavior of the ripples moving across it, the geometry of space controls how energy and matter behave on cosmic scales. So, what do we actually know about that shape? Not everything, but far more than we once did. Astronomers have studied the cosmic microwave background, the faint radiation left over from the early universe. This glow isn't produced by stars or galaxies, it predates all of them. It's the thermal remnant of the universe cooling after the Big Bang. Within this radiation are small variations, tiny temperature differences that act like a data map. These fluctuations reveal clues about the geometry of the universe, not by showing a literal outline, but by indicating how patterns of energy stretch across the sky. From these measurements, current evidence points to a universe that is extremely close to flat. It may not be perfectly flat in an absolute sense, but if there is curvature, it is too small for our instruments to detect so far. That leads to two possibilities. Space might extend infinitely in all directions, or it may curve back on itself so slowly that the full structure lies beyond the region we can observe. This brings us to a critical point. We do not see the entire universe. We only observe the observable universe, the region from which light has had time to reach Earth since the beginning of cosmic expansion. Anything beyond that distance is simply out of range, not because it is hidden, but because its light hasn't arrived yet and may never reach us if the universe keeps expanding rapidly. So when we speak about the universe's shape, we are strictly speaking referring to the shape of the observable portion. The full universe may continue in the same way beyond what we can see, or it might deviate, it might repeat, it might curve. We don't currently know. If the observable region is flat, and if the same geometry extends outward uniformly, then the entire universe could be flat and infinite with no borders, no edges, and no ultimate boundary. But it's also possible that we are observing only a small section of a much larger curved structure. A limited view can easily disguise curvature, just as looking at a tiny part of a huge circle can make it seem straight. In that scenario, the universe could be curved yet finite, looping back on itself in a way we cannot visually grasp. If such curvature exists, you could travel in a straight line and eventually return to your starting point. That would mean there is no physical edge, even though the total volume is limited. Space would be unbounded, but not infinite. A concept that feels contradictory until you think of it like the surface of a sphere expanded into higher dimensions. This leads to a more fundamental problem. How do you measure the size of space when space itself defines what size means? From within the universe, we can measure distances between galaxies and track how those distances change, but we cannot step outside and examine the structure directly. There is no external vantage point. There is no outside at all. The universe contains everything, including the space we use to take measurements. This makes the question difficult. We are embedded within the system we are studying. We can only infer the larger structure from internal observations patterns of light distributions of matter and the behavior of gravity. Even so, geometry matters. The shape of the universe dictates how light moves and how cosmic structures evolve. A positively curved universe, similar to the geometry of a sphere, causes light paths to eventually reconnect. A negatively curved universe, similar to a saddle shape, causes light to diverge more quickly than in flat space. And a flat universe allows light to travel in what we describe as straight lines, straight according to the universe's own geometry. On everyday scales, these differences are invisible. The universe is simply too large, and the curvatures, if it exists, is too slight for us to notice in ordinary life. On the largest scales, these differences in geometry matter. They influence how the universe behaves over billions of years, how quickly it expands, and whether that expansion will continue indefinitely or eventually slow and reverse. The curvature of space also determines whether parallel paths remain parallel, drift apart, or converge. Even when the universe appears calm and unchanging from our perspective, when galaxies shift too slowly for us to notice, and the night sky looks identical for years, the underlying structure is always present. Space has a built in geometry, a framework that shapes how everything within it moves. It defines the stillness we perceive, and that framework may help answer the question we began with. If space has a specific geometry flat curved, or something more complex, then that geometry might tell us whether an edge is possible or whether the concept doesn't apply at all. So far, observations show no sign of a boundary, no indication of a region where space abruptly ends. What we do see is order physical laws, measurable patterns, and a consistent geometric behavior. That structure may be the key to understanding our position in the cosmos and what it really means to exist inside something that might not have a stopping point, yet still invites us to ask where it starts. This leads us to the word edge. It seems straightforward. In everyday life, an edge is where one object ends and something else begins, the border of a table, the end of a book, the rim of a cliff. It's a clean division. Inside is one thing, outside is another. We use edges constantly without thinking about them. The edge of a neighborhood, the edge of a forest, the edge of an idea where clarity slips into uncertainty. Edges make things feel manageable. They define limits and create separation. But when we ask whether the universe has an edge, we're not talking about something that sits inside a larger container. We're asking whether all of space and time could have a boundary of any kind. And if it did, what would lie beyond it? If the universe contains all space, then the notion of an outside becomes problematic. A physical edge would normally separate something from something else. Yet, if the universe includes every region where space exists, then outside can't refer to empty space, because empty space is still part of the universe. The alternative would be a region with no space, no distance, no time, essentially a non-location. This is where our usual understanding of edges breaks down. A boundary only makes sense when there is something on the far side of it. A book ends where the surrounding air begins. A road ends where a field begins. The universe doesn't rest inside a larger environment. It isn't positioned within another medium. It is the environment. So when we ask whether the universe has an edge, we're really posing two different questions. Well, is there a physical limit beyond which space simply does not extend, a literal ending of spatial distance? 2. Is there a deeper kind of boundary, a change in the laws of physics, the structure of space, or the nature of reality that marks a transition from what we understand to something fundamentally different? That second possibility is much more abstract. It wouldn't be a barrier you could touch. It would be more like a threshold in the underlying rules of the universe rather than a wall at the edge of a room. You wouldn't notice it directly, but beyond a certain distance, the rules that govern reality could in principle change. Some theories propose that the physical constants might vary elsewhere, or that space itself could take on a different structure. Certain models of cosmic inflation, the idea that space expanded almost unimaginably fast in the first fractions of a second after the Big Bang, suggest that our observable universe might be just one region inside a much larger multiverse. In these scenarios, each region or bubble could have its own properties, maybe even different dimensions or particle types. If that's true, there could be a kind of boundary, not a physical wall, but a transition zone between one bubble and another. At the moment, though, this remains a hypothetical. There's no observational evidence confirming such boundaries. The word edge also creates a misleading picture. People often imagine it as a destination somewhere you could travel, stand, and look outward. The idea assumes that space is a static landscape with fixed coordinates. But space isn't a rigid backdrop. It expands, it curves, and its behavior influences how objects move through it. Trying to picture the end of space as if it were the end of a road turns out to be too simple. A more useful analogy comes from digital worlds. Consider a video game, not the characters, but the code defining the environment. In one type of game, the world is a finite square, and reaching the boundary means encountering an invisible wall. Nothing exists beyond it because the designers never created anything outside the playable area. That's a strict edge. In another type, the map loops. Walk far enough east, and you eventually reappear on the west side. The space is finite, but it has no terminal point in the usual sense. Or imagine a procedurally generated world where new terrain appears only as the player explores. From within the game, the world feels endless, but from the outside, you know it only exists where the program has generated it. Now bring that back to cosmology. We don't know which, if any, of these analogies matches our universe. We can say that there's no observational sign of a boundary. Light reaches us from objects billions of light years away, and space continues in every direction as far as our instruments can detect. However, all observations have a built-in limit, the speed of light. There is a maximum distance from which light has had time to reach us since the beginning of the universe. That creates a horizon, not an edge to space, but a limit to what we can see. This observability limit is similar to being surrounded by fog. Your visibility stops at the fog line, yet the landscape itself continues. The universe may extend far beyond the region we can observe, or its structure might change somewhere past our horizon. Right now, we simply don't know. This idea of an observable horizon is often misunderstood as a physical boundary, but it isn't one. It's simply the limit imposed by time and the finite speed at which light travels. The universe could extend far beyond that horizon, or it might not. At our current level of knowledge, we can't say. There's another important point that often gets overlooked. Even if the universe did have a true outer limit, it wouldn't be something we could ever physically approach. The obstacle isn't distance, it's the behavior of space itself. The universe is expanding, not expanding into something, but expanding as space. The distance between galaxies increases over time, and the farther away a region is, the faster it recedes from us. Beyond a certain distance, around 16 billion light years, regions of space are carried away by expansion faster than light can travel. This doesn't violate relativity because nothing is moving through space faster than light. Rather, the space itself is stretching. But the effect is the same. You can never reach those regions even if you moved at light speed. They will always recede faster than you can chase them. They are permanently outside our causal reach. This creates another kind of edge, not a physical boundary, but a fundamental limit on what parts of the universe we can ever observe, interact with, or influence. And this limit isn't static. The observable universe grows over time as new light reaches us from regions that were previously hidden. Our cosmic horizon expands, slowly changing the portion of the universe available to observation. So, when you wonder whether the universe has an edge, the answer depends entirely on how the word edge is defined. If you mean a location where space literally stops, we have no evidence of anything like that. If you mean a horizon beyond which we can't see, then yes, but that's a limitation of time and light, not a physical border. And if you mean a transition to a different type of region or different physical conditions, that's possible in some models, but we have no direct confirmation. It may be more accurate to think of the edge not as a spot you could travel toward, but as a conceptual boundary, one that separates the knowable from the unknowable, the visible from the unobservable. It's a relationship between us and the rest of the universe, not a wall waiting somewhere in space. With that in mind, we can turn to one of the most confusing concepts of all infinity. People often use the word casually, saying something took forever or describing the universe as infinitely large. In everyday language, infinity tends to mean a lot or so big it feels endless. But in mathematics and physics, infinity isn't a very large number. It's not part of any counting system. You can't reach it by adding more and more. It doesn't behave like a quantity at all. Infinity is a formal description of something unbounded, something that has no finish line, no terminal value, no point where you can say, that's the end. Even extremely large numbers, billions, trillions, Googles are still finite. They can be written down and compared. Infinity isn't the next step beyond them. It's a different category. It's not a magnitude, but a concept describing systems with no limit. It's a direction rather than a destination. This is one of the reasons people feel confused when they hear that the universe might be infinite. The word makes it sound as though we should be able to quantify it, measure its span, determine how much it contains. But that's not how infinity works. It isn't something you measure directly. It's something you infer from behavior. In mathematics, infinity describes what happens when a quantity grows without any upper limit. It never becomes infinity, it just keeps increasing. Infinity isn't a location you reach, it's the description of a process that doesn't terminate. In everyday life, we don't encounter true infinities. We deal with large numbers, small numbers, long times, short times, but nothing actually without limit. The ocean looks endless, but it has boundaries. The sky feels open, but the stars in it can be counted. So when scientists consider an infinite universe, they're not claiming to have measured something unmeasurable. What they're saying is that as far as current evidence shows, there's no detectable end to space, no sign that it stops or folds back within the region we can observe. This doesn't imply that the universe contains every imaginable possibility. It simply means that the geometry of space might allow it to extend indefinitely, that you could move in a straight line and never return to your starting point, never meet a boundary, and never find a final object marking a limit. However, something can be finite and still have no boundary. The classic example is the surface of a sphere. Its total area is limited, but there's no edge. You can walk endlessly in any direction and never fall off because the surface wraps around continuously. That's a bounded surface without borders. Now imagine a three-dimensional analog, a universe that closes in on itself in higher dimensions. Such a universe could have a fixed total volume, yet be unbounded from the inside. You would never encounter a wall, but the universe would still be finite in extent. In everyday experience, this feels similar to infinity, but the underlying structure is different. This distinction matters. An edgeless universe is not necessarily infinite, and an infinite universe doesn't automatically include everything that can be conceived. When researchers try to determine whether space is infinite, they examine observational clues, how light propagates over large distances, how galaxies are distributed, and especially how the cosmic curvature behaves. Current measurements indicate that the universe is flat or extremely close to flat. If it is exactly flat and not curved in a way that loops back on itself, then the most straightforward interpretation is that space is infinite. Not because we've mapped all of it, but because the geometry implies no natural limit. But our observations only extend to the observable universe, a sphere centered on Earth, roughly 93 billion light years across. That number surprises many people. The universe is 13.8 billion years old, yet the observable radius is far larger because space has stretched while light was en route to us. Even so, this 93 billion light year span isn't an edge. It's simply the distance light has managed to travel since the beginning. Everything beyond that lies outside our sight line for now. Whether that unseen region is part of an infinite expanse or part of a finite but unbounded structure remains unknown. Our current instruments can't distinguish between these possibilities. Many people find infinity difficult because it doesn't behave like familiar quantities. But you don't need to visualize all of it. You can think of infinity simply as the absence of a boundary, a system where there is always more territory beyond whatever point you choose. That's enough to grasp the basic idea. It's also worth clarifying that infinity doesn't imply randomness. An infinite universe can still follow precise physical laws and maintain order. Removing a boundary doesn't remove structure, it just removes the limit on how far that structure extends. And mathematically, infinity itself comes in multiple forms. The set of natural numbers is infinite. So is the set of real numbers between 0 and 1. Yet the second set is larger in a very specific mathematical sense. Infinity doesn't refer to a single size. There are different magnitudes of unboundedness. Mathematicians use these different forms of infinity to understand sets, limits, and continuity, but applying the same reasoning in physics is more complicated. In cosmology, we're not only asking whether the universe is infinite, we're asking what an infinite universe would imply for our position in it, for the long term evolution of space, and for the underlying structure of space time itself. If the universe truly extends without end, then everything we can observe, every galaxy, every cluster, every patch of mapped sky, is just a small region of a much larger whole. And if that larger whole goes on indefinitely, new questions emerge. Would the physical laws remain the same everywhere? Would matter be evenly distributed on enormous scales? Could there be regions unlike anything we see nearby? These are open questions, but we do have some indirect guidance. Measurements show that on the largest scales we can access the universe appears extremely uniform. That smoothness suggests that our local region isn't unusual and that the same general rules probably apply far beyond our observational limits. But we can't verify that directly. Even if infinity fits neatly into our equations, it still functions as a conceptual placeholder, a way of saying that no boundary has been detected and none is required by current models. That doesn't prove a boundary doesn't exist. It only tells us we haven't encountered evidence of one. And this brings the discussion back to edges. If the universe is infinite, it has no edge by definition. But if the universe is finite, yet unbounded, if it closes back on itself in a higher dimensional way, there would also be no edge. In either scenario, space could be edgeless even though its total size might be finite or infinite. This is the surprising part. The presence or absence of an edge tells us very little about whether space is infinite. Everything depends on geometry and topology, not size alone. So, a more productive question might be, what is the shape of the space we inhabit? How does it curve? How do distant regions connect? How does that structure influence the path of light, the flow of time, and the motion of galaxies? These are questions we can begin to answer, not by hunting for borders, but by studying behavior, the expansion of space, the bending of light by gravity, and the patterns in the cosmic microwave background. You've likely heard educators or documentaries bring up a balloon when explaining cosmic expansion. The comparison isn't used because space behaves like rubber, but because it's a practical analogy for a difficult concept. Picture a balloon with small dots inked onto its surface. Each dot stands in for a galaxy. As the balloon expands, every dot becomes farther from every other dot. The dots aren't sliding across the surface itself is stretching. The distance grows not because the galaxies travel away from one another, but because the space between them increases. That simple model captures the essential idea behind cosmic expansion. Galaxies separate over time because the fabric of space is stretching, not because they're rushing outward like debris from an explosion. Galaxies aren't separating because they're being thrown outward like debris. The separation happens because the fabric of space between them increases with time. Each galaxy stays roughly in its own gravitational region, but the distances between those regions grow. The important detail in the balloon analogy is that the surface represents space itself, not the balloon's interior, not the rubber material, but the two-dimensional surface on which the dots sit. That surface has no boundary. You can travel endlessly in any direction along it and never encounter an edge. You would eventually return to your starting point, even though the total surface area is finite. This shows how something can be limited in extent, yet still have no border. As the balloon expands, every point on the surface becomes farther from every other point. There's no central dot and no preferred direction. The center of the expansion is not on the surface at all, it lies in an extra dimension that the two-dimensional inhabitants wouldn't have access to. On the surface itself, the expansion appears uniform everywhere. That's one common misunderstanding. People try to find a center within the expanding surface, but the center is outside the lower dimensional space being used for the analogy. The second misconception is the idea that expansion requires something external to expand into. From the perspective of a being confined to the balloon's surface, the surface doesn't grow into anything, it simply gains more distance everywhere. There is no outside within its own two-dimensional physics. Now transfer that reasoning to our universe, which has three spatial dimensions rather than two. The expansion we observe isn't happening into a void. Space is not pushing into a larger container. The distances between gravitationally unbound objects increase over time because the metric that defines spatial intervals changes. Space expands internally, not externally. This expansion is irrelevant on small scales. Your furniture doesn't drift apart. Planets and stars remain bound. Even galaxy clusters stay together. Gravity and other forces dominate locally, but once you look at scales far beyond galactic neighborhoods, expansion becomes evident. The farther away a galaxy is, the faster it appears to recede. This isn't due to high-speed motion through space. It's the result of the space between you and the galaxy stretching. The balloon analogy is useful, but it's incomplete. Our universe isn't literally a two-dimensional surface. We live in three spatial dimensions, and so far there's no observational evidence for a higher dimensional environment surrounding us. If space-time curves, it does so within its own geometry, not into an external space. People often ask, if the universe is expanding, what is it expanding into? The answer is that expansion doesn't require an external medium. When space grows, the coordinate system that describes positions simply stretches internally. Separation between objects increases even though nothing crosses an outer boundary. It's helpful to think in terms of relative distances. In a room, you can describe a location based on its distance from a wall. In the universe, there are no walls. Position is described only relative to other objects. When the universe expands, those relative distances increase. The grid you'd use to label locations scales up. Imagine again the balloon's surface. A being living on that surface would never find an edge, would never locate a central point, and would never observe a place where the expansion originates. They would simply measure all other points, drifting away from them, regardless of where they stood. This is exactly what we observe in the cosmos. From Earth, distant galaxies recede. If you were standing in any other galaxy, you would measure the same pattern and expansion that looks identical in all directions. This observation is summarized by the cosmological principle, which states that the universe is homogeneous and isotropic on sufficiently large scales. It has the same large scale properties everywhere and in every direction. This principle isn't philosophical preference. It's supported by a variety of evidence, including a galaxy surveys and the uniformity of the cosmic microwave background. The consequence is significant. The patterns we detect in cosmic light and radiation aren't local quirks. They reflect the large scale behavior of space as a whole. What we observe in distant starlight and in the cosmic microwave background isn't just a picture of remote galaxies. These observations act as direct tests of how space itself is structured. They give us information about the geometry that governs expansion. And based on our current measurements, the geometry appears to be extremely close to flat. Flat in this context doesn't mean the universe resembles a sheet of paper. It simply means that on the largest scales, we can probe the rules of Euclidean geometry, hold light travels along paths that behave as straight lines and triangles, add up to the familiar 180 degrees. That doesn't eliminate the possibility of curvature entirely. It only means that if curvature exists, it's small enough that our instruments haven't been able to measure it yet. In comparison, a balloon's surface has positive curvature, and a saddle has negative curvature. Our universe seems to fall near the neutral point, so close to flatness that we don't detect the repeated paths or large scale distortions you'd expect if space curved noticeably over billions of light years. Still, the balloon analogy remains useful. If the universe had positive curvature, it could be finite and edgeless in the same way the balloon's surface is finite, yet boundary free. If it is truly flat and not wrapped back on itself, then the balloon metaphor no longer maps. Cleanly, the universe could extend without limit in every direction. The key point is that the lack of an edge doesn't tell us whether space is finite or infinite. Both possibilities can be edgeless. The analogy also helps clarify that cosmic expansion doesn't require an external environment. Nothing needs to sit outside the universe. Expansion refers to increasing distances between points within space, not to growth into another realm. The container is space-time itself, and stretching occurs internally, not outward into something else. With that in mind, the natural next question is how to classify the overall structure of space. If the distances between galaxies grow, and if light travels through a dynamic expanding geometry, what does that imply about the universe's form? Can we categorize it? Can we predict large-scale behavior? Cosmologists often describe three broad geometric possibilities: flat, closed, and open. These correspond to zero curvature, positive curvature, and negative curvature. They aren't simply abstract mathematical toys. Each geometry produces different predictions for how light spreads, how gravity operates at the largest scales, and how the universe evolves over time. We've covered the basic metaphors: balloons, stretching, space, edgeless surfaces, but the formal models behind them give us something more precise. They allow scientists to compare theory with observation to analyze how the universe's geometry affects the motion of galaxies, the bending of light, and the distribution of cosmic background radiation. This brings us to the deeper question: what kind of geometric structure best describes the universe we inhabit? That's where we're headed next. Let's start with the model that feels most familiar: the flat universe. When cosmologists describe space as flat, they don't mean it resembles a literal sheet or surface. They mean its geometry follows the same rules we learn in basic Euclidean math. Parallel lines never converge or diverge. Triangles have interior angles that sum to 180 degrees. Light travels along straight paths unless gravity from massive objects bends it. In this scenario, space itself doesn't naturally curve inward or outward. Expansion can still happen, and it does, but the growth doesn't cause space to wrap back around or take on a saddle-like shape. In a flat configuration, space extends without bending, and unless another factor restricts it, such a universe is likely infinite. Next is the closed universe. This model curves inward, similar to the surface of a sphere, except in higher dimensional space. It's not the surface of a ball inside some larger container. Instead, it's three-dimensional space, behaving in a way that resembles a spherical geometry. In such a universe, traveling in a perfectly straight line long enough would eventually bring you back to your starting point. The curvature would be spread out so widely that you'd never detect it locally, but on cosmic distances, paths subtly reconnect. A closed universe has finite total volume, yet no boundary. That can feel contradictory, but it becomes intuitive once you recognize that finite and edgeless are compatible. Like an Earth's surface, you can move indefinitely without ever reaching a wall. Space closes in on itself. A closed model also carries the implications about long-term cosmic evolution. It begins with a Big Bang, like any other scenario, but if the inward curvature is strong enough, gravity could eventually counteract expansion. The universe might slow halt and then reverse toward a collapse known as the Big Crunch. It's one possible outcome that fits naturally with positively curved geometries, though not the only one. Then there's the open universe. This model curves outward, similar to a saddle surface. In this case, straight lines tend to diverge, and the angles of a triangle add up to less than 180 degrees. An open universe doesn't reconnect and doesn't loop around on itself. It is unbounded and, like the flat model, extends without limit, but the geometry affects how light spreads and how structures evolve. Expansion in an open universe doesn't halt, it continues indefinitely. Galaxies keep separating energy, density thins out, and over incredibly long timescales, the cosmos grows darker and colder. This leads to a state often referred to as heat death, where usable energy becomes uniformly diluted. These three possibilities, flat, closed, and open, aren't arbitrary categories. They arise directly from Einstein's theory of general relativity. They describe how mass and energy shape the curvature of space-time, how gravity determines trajectories, and how the universe evolves as a whole. Which geometry applies depends on a key factor, the total density of the universe. This includes ordinary matter, dark matter radiation, and dark energy. There is a critical density value. If the actual density matches it exactly, space is flat. If the density exceeds this threshold space, curves inward and is closed. If it falls below the threshold space, curves outward and is open. So, how do we determine where our universe sits on this spectrum? We measure everything we can. We analyze the cosmic microwave background, the faint radiation from the early universe, and examine how tiny temperature variations are distributed. These variations tell us how space was shaped shortly after the Big Bang. We also observe large scale galaxy distributions, study how distant supernovae dim over time, and measure how massive objects bend light behind them through gravitational lensing. All these methods consistently point toward a universe that is extremely close to flat. If there is curvature, it's so subtle that current instruments cannot detect it. That doesn't guarantee perfect flatness or infinite extent, but it tells us that on observable scales, space behaves as though it has zero curvature. And a flat universe is not a simple or empty one. Flatness refers only to the underlying geometry, not to the content. A flat cosmos can still expand rapidly. It can still accelerate due to dark energy. It can still contain galaxy clusters, filaments stretching across billions of light years, and immense cosmic voids. The geometry defines the foundation. Everything else, the structure, the evolution, the matter, and energy within it builds on that foundation. What happens on top of the universe's baseline geometry depends entirely on what fills it, and those contents are not simple. Dark energy, for instance, accounts for most of the total energy density of the cosmos. We still don't know its underlying nature, but we do know what it does. It accelerates the expansion of space. That acceleration doesn't redefine whether the universe is flat open or closed, but it does alter the long term outcome. In a flat universe dominated by dark energy, expansion never reverses. Gravity can't counteract the outward push. The result is a cosmos that stretches indefinitely. Over time, galaxy clusters drift farther apart. More distant systems move out of view as space expands faster than light can bridge the gap. The night sky grows dimmer, stars burn out, black holes slowly lose mass through Hawking radiation and eventually vanish. What remains is a vast, cold, low density space where expansion still operates but very little structure survives. So when someone asks whether the universe is flat, open, or closed, the best current answer is flat, with the caveat that the conclusion is based on measurements that have uncertainties and depend on assumptions about dark energy and early cosmic inflation. These models are part of a broader effort to determine how space is shaped and what that shape tells us about the future of expansion. But one conclusion remains consistent. None of the three geometries require an edge. Flat space continues indefinitely. Open space extends without limit. Closed space curves back on itself. Not one of these models predicts a boundary or a point where space abruptly ends. That brings us back to the misconception many people start with. We tend to imagine an edge, the way we imagine the limits of a table or a map. But the universe isn't an object placed inside a larger environment. It is the environment. If space is flat, it extends without a boundary. If it's open, the same is true. And if it's closed, it wraps back on itself without a stopping point. In every scenario, there is no external region to reach. Because of this, a more productive question than, does the universe end, is what type of space do we live in? How does it behave? What does its geometry allow or restrict? Once we understand the rules that space follows, the issue of edges becomes easier to interpret. And this leads naturally to the next topic. If a space can be finite in total size, yet have no boundary at all, how is that possible? How can a system be limited but unbounded? Earlier, we used the balloon surface analogy, not as a literal model of our universe, but as a way to illustrate an important idea. A space can be complete, self contained, and still lack an edge. At first, this clashes with our everyday experiences. We're accustomed to boundaries, walls, frames, surfaces. Most objects we interact with have clear outlines. A room ends at its walls. A sheet of paper stops at its edges. Even the ocean, despite appearing endless, when viewed from the shore, is contained by Earth's shape. But not all systems behave this way, especially when geometry extends beyond the limits of our intuition. In mathematics, it's entirely possible for a space to be finite in total extent, yet have no boundary. It doesn't extend forever, but there is no point where it terminates. You can move through it indefinitely without encountering an edge, even though the total volume is limited. That is what physicists mean when they describe a space as finite but unbounded. And this type of geometry isn't only theoretically allowed, it may be a viable description of the actual universe. The simplest way to understand this is to begin with low-dimensional examples. Consider a circle. It has a finite circumference that you can measure, but it has no endpoints. If you pick a spot and move along the circle, you'll eventually return to where you started without stopping or changing direction. There's no boundary. The path simply loops. A sphere's surface offers the next step. It is two-dimensional and has a finite total area, yet it has no edge. You can travel across Earth indefinitely, north, south, east, or west, and never encounter a border where the surface ends. You're always moving within the same continuous geometry. Now extend that idea one dimension higher. A three-dimensional analog of a sphere's surface is a space that curves back on itself in every direction. It is not embedded in a higher dimensional container from the perspective of its inhabitants. It is simply the totality of the space. You can move in a straight line forever, and although you may eventually return to your starting point, you never encounter an outer boundary. The volume is finite, but the space is unbounded. We can't visualize such a space directly. Human intuition is based on three-dimensional experiences. So curved three-dimensional spaces are inherently abstract. But in physics, the validity of a model doesn't depend on whether it is easy to imagine. It depends on whether it matches observations, how light propagates, how galaxies are distributed, how fluctuations in the cosmic microwave background appear across the sky. These observations don't show evidence of a boundary, nor do they reveal obvious repeating patterns that would indicate a small closed loop. At the same time, they don't require the universe to be infinite. The mathematics is consistent with a space that curves back on itself so gradually that the loop is far larger than our observable region. A finite but unbounded universe can resemble an infinite one in many practical ways. From any location inside it, there is no apparent limit. You can travel indefinitely without reaching a wall or a discontinuity. Space always appears to continue, but globally, the space closes on itself. This concept overlaps with the balloon analogy, the Earth's surface, and other topological examples. A torus, a donut shaped surface, is another useful model. You can imagine it as a rectangle where opposite edges are joined. Move off the right side and you reappear on the left. Exit the top and you re enter from the bottom. There is no boundary. The space is connected through identifications rather than edges. Now extend that kind of identification to 3 dimensions. Opposite faces of 3 dimensional space connect smoothly not through an external dimension, but through the topology of the space itself. No walls, no outer region, no beyond, just a continuous geometry with internal connections. This is the idea of a finite, unbounded universe, not infinite in volume, not bordered by a wall, but a space with no termination point, defined by the way it connects to itself. This idea has practical consequences for how we think about motion light and the large scale history of the universe. In a finite but unbounded space, a beam of light could, in principle, follow a curved path and eventually return to its point of origin. If the universe were small enough, an observer might see the same galaxy twice, once along a direct route, and once from the opposite direction after the light had circled around the cosmic structure. Astronomers have searched for signatures of this kind of topology, repeated galaxy patterns, matched regions of the cosmic microwave background, or mirrored large scale structures. So far, no such evidence has been found. That doesn't eliminate the possibility. It simply means that if the universe does loop back on itself, the scale of that loop is far larger than the portion we can observe. The return path could be hundreds of billions of light years long, effectively unreachable. For us, a universe of that size would be observationally indistinguishable from one that is truly infinite. This distinction highlights the difference between what a model permits and what we can detect. A universe can be finite, yet appear endless to any observer confined within it. The absence of an observable loop doesn't guarantee infinity. It only reflects the limits of our instrumentation and the age of the universe. This also shows that edges in the physical sense are not tied to size. They depend on structure, how space curves, how it connects, and whether paths close on themselves. In a video game analogy, a world might be coded to generate new terrain, indefinitely creating an effectively infinite map. Another world might wrap in a loop so that walking far enough brings the player back to the starting point. Internally, both experiences feel similar: no visible walls and no apparent boundary. Yet one world is infinite while the other is not. So, when people ask what the universe is expanding into, or whether it has an edge, or whether it is infinite, all of those questions ultimately trace back to one underlying issue: how space behaves when you move through it. Does it curve? Does it connect? Does it close? And none of those behaviors requires a boundary of any kind. A universe does not need a wall to be finite or infinite. What it needs is a specific geometry, a defined way for distance, curvature, and continuity way to operate. That brings us to the natural follow up. If space had an edge, where would it be? One way. People frame the question is, how far must you travel to reach the end of the universe, and what would you expect to find when you got there? But this framing carries assumptions from everyday experience where objects exist inside containers and containers have boundaries. You can walk to the edge of a forest, sail to the edge of a lake, or drive to the edge of a city. Each time you exit one region and enter another, it's intuitive to extend that logics to the cosmos, but the analogy breaks down. Space is not located within a larger medium. It isn't suspended inside another environment. As far as we can tell, space is the framework itself, the set of all positions and directions. It contains everything that can occupy a location. Under that definition, the notion of an outside loses its meaning. If the universe had an edge, it wouldn't resemble the boundary of a field or the rim of a cup. It wouldn't be a location you could travel to, stand near, or even meaningfully point toward. But it's still useful to explore the concept even hypothetically. Consider the fastest traveler. We know a photon, a particle of light. Suppose we allow it to move in a perfectly straight line with nothing to obstruct it. It never slows, never changes direction, and never loses energy to fatigue. It simply continues forward at the speed of light. Where would it go from our perspective? That photon moves through expanding space. It covers distance, but the distance itself is changing as it travels. The space between any 2 points stretches over time. As a result, even though the photon moves at light speed, regions far enough away recede even faster, not because they physically move, but because the metric of space expands. There are regions so distant and receding so quickly that even light can never reach them. These areas lie beyond what is known as the cosmic event horizon. This isn't a wall or a physical border, it's a limit defined by the rate of cosmic expansion. Anything beyond that distance, currently estimated at roughly 16 billion light years away, is permanently outside our ability to influence. No signal we send now will ever reach those regions, regardless of how long the universe lasts. But that horizon is not an edge of space. Beyond it, space continues. Galaxies form, stars shine, and light travels. Those regions are simply causally disconnected from us. If you followed the photon in this thought experiment, it would never encounter a surface or obstruction. It would not reflect stop or turn around. It would simply continue into new regions of space-time indefinitely. Unless the universe is curved in a way that loops back on itself, a scenario for which we currently have no evidence, the photon's path would never repeat. From the photon's own perspective, If we imagine assigning it, things look even stranger. At light speed, time does not progress and distances do not stretch. The entire journey collapses into a single mathematical interval. There is no before or after, just the act of propagation. But from our slower frame of reference, the photon's trajectory spans both space and time. This shows that space contains no obstacles and no endpoints. If an edge existed, it would not present itself as a visible feature. It would not grow larger as you approached. It would not reflect or absorb light. In fact, the familiar concept of an edge becomes difficult to apply. An edge typically separates one region from another, but if there is no outside, then the idea of a boundary loses meaning. Some imagine that space could end in a kind of membrane or interface, a transition from space to not space. But what would that structure be made of? What would support it, and what lies beyond it? If the boundary were physical, it would exist within space-time, and therefore wouldn't be an edge of space at all, just another physical object occupying it. If it were not physical, then nothing could interact with it, making it impossible to approach or detect. Others propose an abrupt termination of space-time, similar to the edge of a video game map. But this creates the same contradiction. What mechanism would prevent particles from crossing that boundary? What would stop light from continuing? Known physics offers no framework in which space simply halts at a position. This leads to a shift in the question. Instead of asking where an edge might be, it becomes more reasonable to ask whether the concept makes sense within the laws of physics. Increasingly, the more productive question becomes, how does space behave? What are the limits on what can be observed or influenced that brings us to a meaningful boundary, the edge of the observable universe? This boundary is not spatial, it is temporal. It is defined by how far light has traveled since the Big Bang, taking into account the expansion of space. This distance, the radius of the observable universe, is about 46 billion light years in every direction. That value does not represent the size of the universe. It represents the extent of the region from which signals have had time to reach us. Beyond that sphere, space almost certainly continues, but we lack any direct access to it. In practical terms, that's a kind of edge. It isn't a barrier, it's a limit on information. A boundary created by the finite age of the universe and the finite speed of light. A horizon we inhabit, defined by the laws of physics. This raises a natural follow-up. If we cannot travel to an edge and cannot see past the observable limit, how do we know that space continues? Is that an assumption or a conclusion based on evidence? We'll return to that question later. For now, the key point is this. If an edge exists, it does not behave like the everyday edges we're used to. It has no surface, no location, no physical signature. It may not exist at all, and if it does, it operates under rules that differ from anything in ordinary experience. Space expands, but not in the way everyday experience might suggest. It's not like a balloon bursting a shockwave, sweeping outward, or an object sliding across a surface. The expansion is gradual and uniform. It happens quietly and continuously. Importantly, this expansion is not motion through space. Instead, it is space itself increasing in scale. Distances grow because the underlying metric of the universe changes, not because galaxies are actively flying outward. The expansion is a geometric effect, not a mechanical one. This process began roughly 13.8 billion years ago. It did not start from a point within a larger environment. Early space appears to have been hot, dense, and nearly the same everywhere. In that early state, no region was central. Expansion occurred throughout the entire volume simultaneously. Every location progressed outward relative to every other, and that behavior has persisted to the present day. It's natural to assume that expansion should slow down over time, the way a stretched spring eventually relaxes, or a launched object eventually decelerates. But cosmic expansion does not follow those analogies. It isn't driven by stored momentum. It's determined by the interplay of mass energy and space-time curvature described by general relativity. The surprising result is that the expansion hasn't been decelerating, it has been accelerating. This conclusion emerged in the late 1990s when astronomers studying distant supernovae noticed something unexpected. These supernovae were dimmer than they should have been based on earlier measurements of the expansion rate. The simplest interpretation was that the universe had expanded more during the light's journey than standard models predicted. In other words, expansion was speeding up, not slowing down. This finding led to the concept of dark energy, a form of energy associated with empty space itself. It isn't a gas or a pressure, it's a built in property of space time, contributing a constant energy density throughout the vacuum. Dark energy doesn't push galaxies apart in the conventional sense. Instead, it alters the geometry of space time so that the scale factor, the measure of cosmic size, increases faster over time. As space grows, the amount of dark energy, which is tied to volume, increases proportionally. That in turn increases the rate of expansion. The effect compounds on itself. This self reinforcing behavior explains why the universe expands faster today than billions of years ago. More space leads to more expansion, and more expansion produces more space. This feedback creates a universe in which large scale expansion does not slow down. The distances between galaxies increase at an accelerating rate. Over time, many galaxies will recede so far that their light will no longer reach us. They will move beyond the cosmic event horizon due to the accelerated expansion of space itself. In such a universe, expansion does not reach equilibrium. It continues indefinitely. The scale factor of the universe increases without reversal, even though locally, within the Milky Way or within our galaxy cluster conditions, appear static and stable. On those smaller scales, gravity counteracts expansion and maintains structure. Expansion only dominates when distances are large enough that gravitational binding is negligible. On intergalactic scales, however, expansion governs the dynamics. Over billions of light years, the stretching of space becomes significant. Over cosmic time, this effect determines the fate of visibility structure and causality. This also makes the concept of an edge irrelevant. Even if one attempted to reach the most distant, observable galaxy by traveling at the speed of light, that galaxy would continue receding. The expansion of space ensures that the separation grows faster than any particle or spacecraft can traverse. This does not violate relativity because nothing is moving through space faster than light. Instead, the metric of space itself changes. The coordinate grid stretches faster than a photon can cross it. As a result, galaxies that we currently observe will eventually pass beyond our cosmological horizon. They will not vanish because they dim or cease to emit light, but because expanding space prevents their future light from ever reaching us. After crossing that threshold, they are permanently unobservable. Ultimately, only the galaxies gravitationally bound to the Milky Way, the local group, will remain visible. Everything else will recede beyond detection. Far in the future, observers within the local group will see an apparently empty universe lacking evidence of distant galaxies, or even the cosmic microwave background. The large scale structure we observe today will no longer be accessible to them. This scenario follows directly from an accelerating universe. If an edge of space exists, it would remain unreachable not because of distance alone, but because space time expansion ensures that the path toward it grows faster than any signal can propagate. The edge, if real, would always lie outside the domain of causal contact. It would not be observable in principle. This is why cosmologists do not treat the edge of the universe as something one could approach. Even if an outer boundary existed, it would lie beyond the region of space to which we have any physical access. Misconceptions about expansion often come from picturing it as an explosion matter moving outward into empty surroundings. But cosmic expansion is not an explosion within a pre existing space. It is an increase in the scale of the space time metric itself. Dark energy, or the energy density of the vacuum, drives this growth. Because that energy remains approximately constant per volume, more volume leads to more total dark energy, which leads to more expansion. This process does not appear temporary. Based on current observations, the accelerated expansion continues, and no mechanism counteracts it on cosmic scales. Dark energy could conceivably change over time, but there is no evidence that it is diminishing or reversing at present. Space expands continuously. It carries galaxies to greater separations. It increases the size of the observable universe. It pushes some regions of space permanently beyond our causal influence. Those regions become inaccessible not because they lack reality, but because the expansion has outpaced our ability to receive information from them. Therefore, when considering whether the universe has an edge, we must also consider whether any such boundary could ever be observed. Even if one existed, it is likely that accelerated expansion would prevent us from approaching it or detecting it. The structure of space-time itself places limits on what can be known independent of the actual extent of the universe. The regions of the universe beyond our cosmological horizon exist outside our light cone. They cannot influence us, and we cannot influence them. This is not a unique situation. It applies to every location in the universe. Every galaxy, star, and planet has its own observable region, defined by the same rules of space-time and expansion. Some of those regions overlap, others do not, and never will. This is an inherent consequence of cosmic expansion. There are galaxies whose light will never reach us. They are not invisible because they lack luminosity, but because they are receding faster than light can compensate for due to the expansion of space. Even over an infinite amount of time, their photons will not cross the growing distance. They are not concealed behind matter or dust. They are beyond causal contact. If new galaxies formed in those regions, if stars ignited, if biological or technological activity occurred, none of it would ever become observable to us. The limitation is not technological, it is a property of space time itself. Despite these strict boundaries, we can infer conditions beyond our observable region indirectly. Measurements of the cosmic microwave background, the distribution of galaxies, and the growth of large scale structure all provide constraints on the nature of regions we cannot observe. Current evidence indicates that the universe beyond our horizon is likely similar to what we see within it. Large scale homogeneity and isotropy, the principles that the universe is uniform on the largest scales, are supported by observations. This does not mean the universe must be identical everywhere. It only means that the simplest and most consistent interpretation of the data is that the same physical laws and large scale structures extend beyond our current view. However, the universe could deviate from those expectations outside our observable boundary. It could differ in curvature density or topology. It could undergo transitions or changes we cannot detect. These possibilities remain open because the limits of observation are fundamental, not temporary. The observable universe is not a technological horizon, it is a causal one. No matter how long we wait or how advanced our instruments become, certain regions will remain inaccessible. This is part of what leads to theoretical models that include regions of spacetime beyond our own, such as the multiverse hypothesis. In some versions of inflationary theory, rapid early expansion produces separate pockets or bubbles of spacetime that stop inflating at different moments and develop distinct physical conditions. These regions are causally disconnected from one another. They expand independently, and the space-time between them grows too quickly for any signal to travel across. If this model is correct, such regions may be numerous or even infinite, but they are permanently unreachable to us. Thus, when we ask what lies beyond the observable universe, the range of answers includes conditions very similar to our own regions, with altered laws of physics or no further structure at all. What is clear is that space does not end at the boundary defined by our horizon. That boundary is not a physical edge, it is a limit set by the travel time of light and the expansion rate of space. The universe extends beyond it, and its continuation emphasizes an important point even at the largest scales accessible to us. Our vantage point is surrounded by more than we can ever observe. The limitation is not a matter of perspective, but a built-in feature of space-time. In everyday experience, most systems have a center or point of origin. A room has a midpoint, a circle has a center, and many structures grow outward from a clearly identifiable core. This intuition often leads to a common misunderstanding of the Big Bang. People imagine it as an explosion occurring at a specific location in space, with matter expanding outward from a central point. But this is not how the Big Bang is understood in modern cosmology. The Big Bang was not an explosion within space. It was the rapid expansion of space itself. It did not occur at a single coordinate. It occurred everywhere. Space time and the energy within them were created in that early state. There was no existing volume into which the universe expanded. Instead, distances between points grew because the underlying geometry changed. This is why the universe has no center. Every region of space originated from the same early conditions. Expansion happened uniformly, not outward from a specific location. Because of this, every observer in the universe sees surrounding galaxies receding from their position. The same effect would be observed from any galaxy. The expansion looks isotropic from all vantage points, and no point is singled out as the origin. This leads to a useful distinction. Each observer is at the center of their observable universe, not because the cosmos is centered on them, but because their observations are limited by the distance light has traveled since the Big Bang. The center in cosmology is not a physical position. It is a viewpoint defined by the observer's light cone. Our maps of the universe naturally place Earth at the center because all measurements originate here. If we observed from a distant galaxy, our maps would again place our own position at the center. This symmetry is a consequence of homogeneity. The universe is similar at large scales everywhere. In isotropy, it looks the same in every direction. These principles are strongly supported by data. The cosmic microwave background, CMB, the relic radiation from the early universe, shows nearly uniform temperature across the sky. There is no evidence of a directional gradient or a privileged region. Small fluctuations in the CMB are statistically consistent with a universe that has no geometric center. This uniformity is one of the main motivations for inflation theory, which proposes an early period of extremely rapid expansion that smoothed out irregularities and produced the even distribution we observe today. The question, where did the Big Bang happen, therefore has a specific answer. It occurred everywhere that space exists. It was an event in time, not an explosion at a location. The concept of before the Big Bang may also lack physical meaning because time itself began with that early state. Models that attempt to describe earlier conditions, such as cyclic universes or bounce scenarios, still operate within the same framework. Our observable universe does not have a central point from which space expands. Modern cosmology consistently shows that the universe has no center in space and no preferred direction. Expansion occurs uniformly throughout spacetime, and the large-scale structure we observe is consistent with a universe that is homogeneous, isotropic, and without a spatial origin. In its earliest moments, according to inflation theory, the universe expanded at an extreme rate, faster than the speed of light. Not because matter was moving through space at that speed, but because space itself was stretching. This rapid expansion smoothed out density variations and produced the large-scale uniformity we observe today. The near uniformity explains why the cosmic microwave background looks the same in all directions, but it also makes it more difficult to determine what lies beyond the observable region or what global properties the universe has. Without visible irregularities to trace it, becomes harder to infer the full shape or topology of spacetime. These questions about curvature topology and the global structure of the universe do not rely on a physical center or boundary. They rely on how distances behave, how geodesics curve, and whether space closes on itself or continues indefinitely. To analyze them, one must abandon the intuitive expectation of a central point or an originating location. In modern cosmology, no such point exists. The expansion is uniform, and the geometry is described by relationships between spatial coordinates, not by reference to a privileged origin. The absence of a center does not remove structure from the universe. Local physics still applies, measurements remain valid. Galaxies evolve, stars form, and matter follows gravitational dynamics. The lack of a geometric center simply reflects the homogeneity and isotropy of the large scale cosmos. Once we stop searching for a central position, the behavior of expansion and the implications of curvature become easier to interpret. The focus shifts from where the universe began to how space-time evolved, and from where it might end to whether such an end exists in the first place. This naturally leads back to the concept of infinity, not as an abstract mathematical symbol, but as a potential physical property of space-time. In mathematics, infinity indicates unboundedness rather than a specific value, and in cosmology, it may describe the extent of space. If the universe is spatially infinite, then no matter what direction one chooses, space extends without limit. There is no location where it terminates, no outer surface, and no return path created by curvature. That is one possible model. Current measurements, including observations of the cosmic microwave background, large-scale galaxy distribution, and gravitational lensing, indicate that the universe is flat or extremely close to flat. A perfectly flat universe with a non-looping topology would be spatially infinite. In that case, our observable universe would represent only a finite region within an unbounded volume. The horizon we see defined by the distance light has been able to travel since the Big Bang does not correspond to a physical boundary. It is simply the limit of available information. If space is infinite, then geodesics extend indefinitely. An object traveling in a fixed direction would not encounter any form of outer boundary. The reach of observations would still be limited by the speed of light, by cosmic expansion, and by the finite age of the universe, but the spatial manifold itself would not terminate. In such a model, the number of galaxies, stars, and large-scale structures is not just extremely large, it is unbounded. The total mass energy content of space would also be unbounded, although density values would remain finite. This possibility has significant implications for cosmology, but it remains a model, not a proven fact. Observations currently allow for both an infinite universe and a very large finite universe with a topology too large for us to detect. Distinguishing between these scenarios requires more precise measurements of curvature and potentially new methods for identifying global patterns. In an infinite universe, The number of galaxies is not simply very large, it is unbounded. The count cannot be completed or exhaustively cataloged because there is no finite total. The same applies to stars, planets, and potentially habitable environments. This leads to a statistical implication if space is infinite and the types of matter and physical configurations are finite, then specific arrangements of particles must repeat at sufficiently large separations. The repetition need not occur within any observable region, and these configurations would not be located anywhere near one another. But mathematically, with a finite set of building blocks and an infinite volume, recurrences become unavoidable. This doesn't imply identical copies in a literal or science fiction sense. It follows simply from combinatorics in an unbounded system given unlimited volume, even extremely improbable arrangements eventually occur. In practice, none of these hypothetical repetitions are accessible. The separations would exceed the distances light could cross in the entire lifetime of the universe, even over trillions of years. They remain theoretical consequences of an infinite model rather than observable structures. This version of infinity, arising from flatness and continuous expansion, reframes how we think about spatial extent. Space is not defined by boundaries, but by behavior, specifically the absence of limits. In such a context, one doesn't reach infinity, one simply moves through space that has no endpoint. Although gravity shapes motion and large scale structure, the spatial manifold itself imposes no terminal distance. A traveler moving indefinitely in a fixed direction would never encounter a terminating feature. Infinity is therefore not a location, but the absence of any spatial bound. It also changes how several cosmological quantities must be defined. An infinite universe has no total energy. Such a value cannot be computed. There is no meaningful global average across the entire volume, only averages taken over finite regions. No matter how large the observed sample becomes, it remains a subset of an unbounded whole. The full structure is never reached. When this perspective is adopted, questions about the universe's total size or the location of an edge lose relevance. More productive questions concern how space behaves, how matter clusters, how expansion evolves, how curvature influences motion, and how geometric rules shape large scale structure. In an infinite universe, geometry and physical laws determine what is possible. Boundaries do not play a role. This brings us to another recurring question. If one travels long enough in a straight line, is it possible to return to the starting point? At first glance, this seems like a question about distance. In cosmology, however, it is a question about topology, the global connectivity of space. It concerns whether the universe closes on itself or continues indefinitely. Space appears flat on large scales. Triangles formed by distant galaxies behave according to Euclidean geometry, and light paths are straight except where curved by gravity. But flatness alone does not determine whether space is infinite. A flat universe can still be finite if it has a compact topology. A familiar example is a two-dimensional square with opposite edges identified. A person walking off one side would reappear on the opposite side. Locally, the space is flat. Globally, it loops. A three-dimensional version of this structure is possible. In a three-torus configuration, opposite faces of a cube-like region connect, creating a finite but unbounded volume. A traveler moving straight ahead could eventually reappear at the starting point, not because the path curves, but because the space wraps around. Light in such a universe could also trace closed paths, making it theoretically possible to observe repeated patterns in the sky, multiple images of the same objects arriving from different directions. Scientists have searched for this type of evidence, especially in the cosmic microwave background. A looping topology would produce matching patterns, specific correlations, or repeated circles of temperature fluctuations in different regions of the sky. So far, data from missions such as WMAP and Planck show no convincing signs of such repetitions. This suggests that if the universe has a compact topology, its characteristic size exceeds the observable region. The loop could exist, but be too large for any light to have completed a circuit since the Big Bang. In that case, the universe could be finite in volume, yet effectively indistinguishable from an infinite one. The topology would remain undetectable simply because the observable sphere is too small relative to the global structure. At this point, we reach a familiar conclusion. A looping topology remains possible, yet potentially undetectable. The structure could exist, but the evidence may lie outside the observable horizon. Even so, the concept persists because a universe that loops is not only mathematically reasonable, but also physically distinct in ways that are difficult to overlook. In a finite, closed space, motion in a straight line would never lead to an edge. The path would not reach a boundary or a new region of space. It would eventually return to the starting point after an extremely long interval. Whether such a return would be recognizable is another question. In an expanding universe, any full circuit would take longer than the age of the cosmos. By the time the path closed, the original location would have undergone significant changes. Galaxies displaced, stars evolved, and the overall structure altered by expansion. Even the coordinate system itself would have stretched enough that the returning point would bear little resemblance to its initial state. Light would behave similarly. In a looping universe, photon trajectories could circle the entire structure. Their paths might intersect and re-enter the observer's field of view from different directions. This could, in principle, allow a galaxy to be seen multiple times from distinct angles, including views corresponding to earlier epochs. Such a phenomenon would generate identifiable patterns in the sky, repeated temperature fluctuations in the cosmic microwave background, or duplicated large-scale structures. Although current measurements do not reveal these signatures, the available data is not perfect. Subtle correlations could still be present, but unresolved, or the characteristic size of the loop could be far beyond the observable region, making detection impossible with current instruments. If such a loop exists, it would imply that the universe is finite in volume, yet lacks boundaries. There is no perimeter, no final region, and no exterior. Every direction leads eventually back into the same space. This changes how we consider global quantities. In an infinite universe, total mass energy or entropy cannot be defined. In a finite but unbounded universe, those values would be finite because the system has a fixed volume determined by geometry, not by walls or borders. A looping universe does not imply smallness. It implies a specific global structure. It behaves like a complete system whose extent is established by topology rather than by physical constraints. Another possibility involves a closed universe shaped by positive curvature. Instead of a flat toroidal topology, this scenario corresponds to a hyperspherical geometry, a higher dimensional analog of the surface of a sphere. Space remains finite and unbounded with no edges, but the closure results from curvature rather than identified boundaries. In such a model, all geodesic paths eventually meet, similar to how straight paths on Earth's surface eventually converge, but occurring in three spatial dimensions rather than two. That type of universe has a different long-term behavior. In some models, with positive curvature expansion, eventually slows, halts, and then reverses, leading to a contraction phase, a return toward high density, sometimes described as a big crunch. Current observations, however, show no indication of such a slowdown. Instead, the expansion is accelerating, driven by dark energy. Under those conditions, long-term contraction becomes unlikely. Even so, the geometry remains relevant because a looping structure, if it exists, describes how the global system fits together regardless of the universe's fate. This brings us to another persistent question. If the universe neither loops nor ends, and instead extends without limit, then what surrounds it? The question is difficult to avoid, even though it has no straightforward answer. It feels intuitive that an expanding system must occupy a larger environment. We are accustomed to nested structures, rooms within buildings, buildings within cities, physical objects confined by larger physical spaces. When we learn that the universe expands, it is natural to picture it expanding into something as if space behaves like an inflating balloon positioned inside a larger region. But this analogy fails at the key point. The universe is not an object expanding inside a pre existing room, it is the spatial framework itself. The balloon analogy is useful only within boundaries. It demonstrates how surfaces can be finite, yet unbounded, but the metaphor still assumes an external space in which the balloon exists. In actual cosmology, there is no outside, not in any direction, not in any dimension accessible to the physics we understand. Space does not sit within a container, it defines the container. When space expands, it is not filling an external void, it is increasing the distances between points within its own geometry. If you ask, where is the universe located? The correct answer is that the question has no reference frame. The universe is not located inside a larger coordinate system. It is the totality of all coordinate systems. Asking where expansion occurs leads to the same issue. Expansion does not occur into external space. It occurs within space as the metric that defines distances changes. The idea of expanding into something is borrowed from everyday experience, not from the physics of space-time. This is difficult to reconcile with intuition because every structure we encounter has limits. Every physical object has a surface. Every room has walls. But if current theoretical models are correct, the universe has no external region at all. You cannot exit it, travel beyond it, or view it from the outside. Even a finite universe with a looping structure does not require an external container, just as the two-dimensional surface of a sphere does not require a surrounding box to be complete. Some theoretical frameworks do propose the existence of additional spatial dimensions. In certain higher dimensional models, our universe could be a three-dimensional brain embedded in a larger dimensional space. But even in those cases, the outside is not ordinary space, and it is not accessible from within. It would operate under different physical conditions, governed by rules unlike those that apply inside our universe. Moreover, none of these models are confirmed. They are mathematically motivated, but experimentally unverified. Based on current evidence, the best supported conclusion is that there is no outside in any conventional sense, not a region, not a higher space similar to ours, not a surrounding environment. If anything lies beyond the universe, it is not a place that exists within the framework of space and time. And when we use the word nothing, we cannot describe it as empty or dark or vacant. Those terms still assume spatial properties. Real nothing in this context refers to the absence of space-time itself, the absence of dimension location, extension, direction, and duration. Such a state is not reachable, not observable, and not positioned adjacent to anything. It simply lacks all physical meaning. This idea often feels unsatisfying. It seems as though the discussion is avoiding the question, but the limitation is conceptual, not evasive. Imagination relies on spatial context. Without space or time, there is no framework into which an outside could be placed. The issue is not that a boundary is hidden. The issue is that the concept of a boundary does not apply. This understanding leads to an important conclusion. Whether the universe is infinite or finite, it is self-contained. It does not require an external environment. It does not expand into a larger domain. It establishes its own structure and its own limits or lack of limits. Any attempt to imagine what lies outside the universe becomes a question about something that by definition does not exist within the physics we can describe. That does not end the inquiry, it redirects it. Instead of asking what lies beyond everything, we turn toward more productive questions. What conditions produced space-time? How did the laws of physics arise? If the universe had a beginning, what does a before mean when time itself may have originated in that event? These questions shift the focus from external boundaries to the origins of the system. They guide us toward the physics of the early universe rather than toward an imagined exterior. And addressing them requires moving from geometry to initial conditions, from the structure of space to the processes that brought it into existence. When we talk about edges, we usually imagine them as locations, a fence marking the limit of a yard, the end of a hallway, a shoreline where land gives way to water. But time raises a different kind of boundary. Not a physical border, but a conceptual one, a beginning, an endpoint, the moment when history starts. And from that comes one of humanity's oldest questions. Did time itself ever begin? And if so, what precedes a beginning? We naturally picture time as a line extending in both directions. We travel along it without stopping, always moving forward. It seems intuitive that the line should stretch behind us just as far as it stretches ahead. Yet in modern cosmology, the evidence points to a start. According to our best measurements, roughly 13.8 billion years ago, the universe entered a state where expansion began, matter formed, and radiation decoupled. That early stage, what we call the Big Bang, wasn't an explosion in empty space. It was a transformation of the entire system. Space expanded everywhere at once, and the conditions we associate with time, motion, and causality emerged. At that moment, time as we understand it appears to begin, not because information before it is missing, but because the concept of before may have no reference. There is no timeline extending into an earlier era. No prior tick of a clock, no coordinates preceding the earliest measurable moment. This introduces a kind of boundary not in space, but in time itself, a starting edge. But what exactly does it mean for time to start? The question is difficult because our language and intuition rely on sequences, one event following another. When something begins, we instinctively ask what triggered it, what came immediately prior, what conditions allowed it. However, if time itself originates at the Big Bang, then such questions lose meaning. Before only applies when a temporal dimension exists. If time has a starting point, then there literally is no before for anything to occur in. Some physicists describe this by analogy to a coordinate system that simply stops at one end. You can assign time values after the Big Bang, counting forward into the present, but the axis doesn't extend into negative territory. Not because a boundary blocks it, but because the coordinate is undefined beyond that limit. Other approaches consider an even deeper possibility. Perhaps time is not fundamental at all. Maybe what we call time emerges from something more basic, an underlying structure in which change exists, but temporal order does not. In several quantum gravity models, the earliest universe isn't described as progressing through time, but as existing in a state without temporal meaning, no sequence, no earlier or later, just a set of probabilistic configurations. In that view, the Big Bang represents a transition rather than a moment of creation, a phase shift similar in spirit to ice, becoming liquid, except the change is from a timeless state into one where time becomes a meaningful variable. In that framework, time doesn't appear suddenly or switch on like a light. Instead, it gradually comes into existence as the early universe stabilizes. Once conditions allow it, time begins to function as a consequence of increasing entropy, the natural spread of disorder, and the resulting directionality of information flow. The arrow of time in this view isn't a fundamental rule, it's a byproduct of how the universe evolves. Other approaches consider a very different picture. The universe might not have started with a singular beginning at all. Some models describe a cosmic bounce. in which a prior universe underwent contraction before transitioning into the expansion phase we inhabit now. In such scenarios, something existed before the Big Bang, but it wasn't part of our timeline. It belonged to a previous phase in a larger recurring cycle: collapse, expansion, collapse again. Time doesn't rewind, but the universe oscillates. More speculative ideas go even further and suggest that time itself could be cyclic. Not cyclic in the trivial sense of clocks repeating their numbers, but in the geometric sense that after enough temporal progression, the path through time reconnects with its starting point. You wouldn't reach a final moment, you'd eventually loop into the beginning again. These concepts remain unconfirmed, but they each attempt to address the same puzzle: how does a beginning occur if before doesn't exist? In everyday life, we experience a very clear temporal direction. We retain memories of the past, never of the future. Causes precede effects. Yet the core equations of physics do not require this one-way flow. They operate symmetrically forward or backward in time, is mathematically equivalent. So why does our experience contradict the symmetry of the laws? It comes down to the starting conditions of the universe. The earliest cosmos was remarkably ordered, low entropy, uniform, hot, and dense. From that state, entropy inevitably increased. Structures formed, radiation, dispersed, galaxies assembled, information spread out. And as disorder grew, the arrow of time emerged. Our sense of past and future is tied to that progression. Had the cosmic initial state been different, our perception of time, or whether we perceive it at all, might have been radically altered. This brings us back to the idea of a temporal boundary. Not a physical edge or a specific moment you could approach, but a conceptual limit, a region where time is not yet defined. It's not a location, it's not a wall, it's more like a threshold where the notion of earlier simply stops being meaningful. As time emerges and begins to flow, dynamical processes appear. Particles move, light behaves predictably, cause and effect become possible, and expansion unfolds. Some theoretical models smooth out the Big Bang entirely. Instead of a sharp singularity, they replace it with a transitional era where the equations flatten out and time gently emerges from a state that cannot be described in conventional terms. There is no abrupt starting instant, only a limit to how far our mathematics can be extrapolated. Beyond that limit, the theories stop applying, not because something is hidden from view, but because the very concepts we rely on, time sequence, causality, no longer exist. This isn't a failure of understanding. It reflects what time fundamentally is: a structure we inhabit, a parameter that becomes meaningful only after certain physical conditions arise. Time has no spatial edges. It may not have a before. It might not conclude in a simple ending. And it might not be a straight line at all, but a more complex structure we haven't yet discovered. Whatever its nature, we exist inside it. And if the universe has no external space, and if time may have no prior moment, then perhaps some of the limits we assume about beginnings, boundaries, and outside are expectations left over from everyday experience, not actual features of reality. If time has a beginning, it's reasonable to ask whether it might also have a final limit, whether the entire cosmic system, including space and time themselves, could eventually stop. The question has existed for as long as people have wondered how the universe started. If there was a first moment, could there one day be a last? To answer that, cosmologists look at how the universe evolves under the laws of gravity, thermodynamics, and quantum theory. Historically, three broad possibilities were considered. 1. The Big Crunch. In this scenario, gravity eventually reverses the expansion. The universe slows, halts, and begins contracting. Galaxies would draw together again, distances would shrink, and temperatures and densities would rise. Over immense timescales, the cosmos would collapse back into an extremely hot, dense state. It would be a temporal mirror of the beginning, not an outward expansion, but an inward implosion. Some versions lead to a singularity, others allow a transition into a new phase. However, current observations contradict this pathway. Expansion is not decelerating, it is accelerating to the big freeze. This is the outcome most consistent with present data. If dark energy remains roughly constant, the universe will expand forever. As space grows, galaxies drift apart, star formation declines, and existing stars burn out. Over trillions of years, the universe becomes increasingly cold and dilute. Black holes evaporate. Particles decay if they are unstable. Thermal energy spreads so widely that meaningful physical processes cease. It is not an abrupt ending. It is a long period of diminishing activity. Time keeps moving forward, but events become rare to the point of near non-existence. In such a future, time persists, yet it loses practical significance, because nothing changes enough to differentiate one moment from another. Duration continues, evolution stops. 3. The Big Rip. This possibility arises if dark energy's strength increases with time rather than remaining constant. If the repulsive effect that drives expansion grows without bound, it can eventually overwhelm not only the gravitational pull between galaxies, but also the forces that hold galaxies, stars, planets, molecules, and even atomic nuclei together. In that case, the accelerating expansion would tear apart structures in sequence, distant galaxies first, then nearby ones, then stellar systems, then planets, then matter itself. Ultimately, even space-time intervals could be pulled apart. This endpoint is catastrophic and rapid, but current measurements do not indicate that dark energy is evolving in that direction. The evidence favors the relatively stable form of dark energy. Still, our understanding of dark energy is incomplete. Future data might modify these projections. Ma, I dis- as- dis- There is also a more subtle and less intuitive possibility: vacuum decay. According to quantum field theory, the vacuum, the lowest in energy state of space, might not actually be the true minimum. If our universe occupies a false vacuum, it could at any moment transition to a lower energy configuration. Such a transition would form a bubble of new vacuum that expands outward at the speed of light. Everything inside would be remodeled according to the physics of that lower energy state, which may not allow atoms' chemistry or familiar forces to exist. It would arrive without warning, because no signal can outrun the front of the bubble. To any observer, the transition would be instantaneous. This scenario is speculative, but not ruled out by known physics. If it occurs, nothing would survive to describe it. But vacuum decay, if it is possible at all, falls into the category of theoretical outcomes rather than actionable predictions. It is not something we can prepare for measure in advance or detect as it approaches. It is simply one logical endpoint allowed by our current understanding of quantum fields. Meanwhile, the universe continues to evolve in familiar ways. Stars still form galaxies, still merge and disperse planets, still rotate, and environments still support the kinds of questions that lead us to think about cosmic futures in the first place. The fact that we can ask how the universe might end indicates that we live during an interval when large scale structure exists and processes still unfold. Whether the universe eventually collapses, freezes, or undergoes some other transformation does not change the fact that our own existence occupies only a narrow span of cosmic time. Even if time continues indefinitely, individual lifetimes do not. On human scales, what matters is that we exist in an epoch where the universe remains dynamic, where stars shine, information circulates, and physical processes continue to operate within ranges we can observe and understand. This leads to a broader point. Infinity, whether in space time or mathematical structure, is not solely a remote or abstract concept. In many ways, it is embedded in ordinary experience. Each moment you observe belongs to a sequence without a known upper bound. Every physical distance you measure, from the size of a room to the length of a street, lies within a continuum that, as far as current physics can describe, can be subdivided indefinitely. You do not need to cross the universe to encounter an infinite framework. It is already implicit in the tools you use to analyze the world. Consider a simple line segment. It has a finite length, yet mathematically it contains an unbounded number of points. You can divide it repeatedly, halves, quarters, eighths, and so on, without reaching a smallest possible interval. Classical physics treats space and time similarly. Between any two spatial points lies another. Between any two instants lies another. Timekeeping devices merely mark intervals. They do not discretize time itself. Even if future theories impose a minimum meaningful scale, such as the Planck length or Planck time, that would represent a theoretical limit of description, not necessarily an intrinsic boundary in nature. At present, the continuity of space and time is one of the core assumptions in general relativity and quantum field theory. The same reasoning applies to quantities in the physical world. A grain of sand contains more atoms than one could count manually, and a small volume of air contains trillions of molecules in constant motion. These magnitudes arise from the sheer number of microscopic components that make up everyday matter. We routinely interact with systems that contain quantities far beyond intuitive comprehension, and we rely on mathematical concepts, limits, continua, infinitesimal divisions to describe them. In our daily lives, infinity functions less as a distant cosmological idea and more as a background principle. The number line extends without bound. Real valued measurements rely on continuous scales. Function can be defined over unbounded domains. Even simple shapes such as squares or circles are formally described using infinite sets of points and continuous symmetries. The mind adapts to these abstractions early. Once a person understands that counting has no maximum or that any length can be subdivided indefinitely, they have accepted the concept of an unbounded process. Infinity in this sense is not speculative. It is part of the foundation of arithmetic geometry and measurement. In science, it appears whenever we study scales, both extremely large and extremely small. Cosmology invokes the possibility of infinite spatial extent, while particle physics and quantum mechanics probe structures with no established lower limit. Whether the universe ultimately contains a smallest length or an edge in space or time remains an open question, but the mathematical framework we use to study it relies on continuous structures and unbounded sets. Thus, infinity is not something remote or inaccessible. It is embedded in the frameworks we use to describe the world and in the processes we observe every day. It emerges not only in the largest scales of cosmology, but also in the smallest scales of matter and measurement. The mathematical description of space and the physical laws built upon that description rely fundamentally on continuous quantities. When you draw a circle, you invoke p a number with no finite decimal expansion. When you calculate velocity, you divide one continuous quantity distance by another time. Both quantities are modeled as having infinite resolution. Even routine technologies, such as digital communication or display systems, depend on underlying physical processes that operate across scales too fine to enumerate. In this respect, the concept of infinity is not remote. It is embedded in the frameworks used to model both natural and engineered systems. Every coordinate, every interval of time, every geometric object described by mathematics contains an unbounded set of substructures. This perspective shifts the usual line of inquiry. Instead of asking how far away the infinite might be, one begins to ask how any finite measurement or finite system can exist within a mathematical framework that in principle admits unbounded divisibility. A finite object is always represented within an infinite continuum. A finite duration is composed of infinitely many intermediate instants. A bounded region of space contains infinitely many points. The presence of these continuous structures in the foundations of physics leads naturally to broader questions. Questions not only about the extent of the universe, but about the nature of description itself. The same continuity evident in large-scale cosmology appears at small scales in geometry, measurement, computation, and physical behavior. Recognizing this continuity makes the larger cosmological questions feel less detached from everyday experience. The infinite does not need to be located at the far edge of the cosmos. It appears in the mathematics that defines motion location and duration. The critical task is not to locate infinity as a place, but to understand how physical laws operate within structures that assume unbounded mathematical precision. This recognition leads to a shift in emphasis. The universe becomes less of a location and more of a system defined by rules, constraints, and relationships. This shift becomes clearer when we consider the nature of physical law. It is convenient to view the universe as a machine composed of matter, energy, and space time interacting through deterministic or probabilistic rules. That model is effective for describing how systems evolve. However, when we investigate more fundamental questions, questions about why laws take their particular form, or what underlies the consistency of those laws, the machine analogy begins to lose explanatory power. At the deepest levels, the universe resembles a relational structure more than a mechanical assembly. The behavior of particles can be described in terms of symmetries, invariants, and constraints rather than intrinsic physical substance. Quantum field theory characterizes particles as excitations of underlying fields, patterns, rather than standalone entities. General relativity describes gravity not as a force, but as geometry relationships among space-time intervals, rather than interactions between objects. Many modern approaches to unification restructure physical law around principles of information, symmetry groups, or mathematical consistency, suggesting that the fundamental layer of reality may be an abstract structure from which the familiar properties of matter and space-time emerge. This does not imply that the universe is imaginary or illusory. It means that at the most basic level, accessible to theory, physical systems may be best understood in terms of the mathematical structures that constrain and define their behavior. The universe in this view is not a machine with parts assembled from pre-existing materials. It is a consistent system governed by rules that give rise to the phenomena we observe. Mathematics is not an external language imposed on physics, but a set of structures that physics itself appears to instantiate. Nobody invented arithmetic. We discovered the relationships that numbers already obey, how addition works, how multiplication distributes, how geometric shapes behave, how equations balance. These patterns were valid long before anyone wrote them down. They are not human constructs, they are properties of a deeper logical structure. Physics appears to operate in the same way. As our understanding improves, the universe consistently aligns with mathematical rules, not approximately and not by convenience, but with exact correspondence. The equations that describe gravitational behavior also describe motion. The same symmetry principles that classify elementary particles also determine how fundamental forces operate. Physical processes repeatedly reduce to patterns that mathematics already captures. This alignment is not accidental. It indicates that the universe is not simply a region where matter occupies space. It behaves like a system governed by relational rules. The fundamental constituents of reality do not appear as isolated objects. They appear as interactions, constraints, and consistent relationships. Rules do not require spatial form to exist. They only require definition. They can be expressed through equations encoded in symmetries modeled as information. This leads to a broader interpretation. The universe may be a particular instance of a deeper mathematical structure, not metaphorically, but in a literal sense. The behavior we call physical law, the expansion of space, the motion of particles, the evolution of fields, may be the result of a specific set of logical constraints playing out over time. In that perspective, the universe functions like the output of a rule set a lawful unfolding of consistent relationships. This idea appears in multiple scientific frameworks. One is the mathematical universe hypothesis, which states that reality is not simply described by mathematics, but is itself a mathematical structure. All mathematically self consistent structures would exist in this broader sense, but we inhabit one capable of supporting complexity, stability, and observers. Another approach treats the universe as an informational system. In these models, particles, fields, and interactions are not foundational substances, but expressions of encoded relationships. Bits of information updating according to specific rules. Space, time, and matter become emergent features of an underlying informational framework. Not the kind of information stored in computers, but something more fundamental, simple, yes or no facts about the state of reality. Every interaction, every transition, every connection can be described as part of an underlying logical network. In that view, matter isn't a basic ingredient. It's an outcome, a configuration produced when these rules interact with themselves. Even space-time in several modern theories might not be a primary component of reality. It could be emergent, something that appears only when enough information is organized and processed in particular ways. Temperature works similarly. A single atom has no temperature, but when many atoms move and collide, temperature becomes a measurable property. Space-time may be the same type of phenomenon, a large-scale pattern arising from countless small-scale logical interactions. This idea isn't fringe speculation. Much of current theoretical physics moves in this direction. Attempts to unify quantum mechanics and general relativity routinely explore models where information and structure are fundamental and space-time itself is derived. These approaches remain abstract, but they still yield testable predictions. They still point to observable consequences, and they still build models that can be compared with real data. In this sense, the universe might function like a self-consistent thought, not because it's imaginary, but because its foundation appears closer to formal structure than to mechanical substance. Once the rules are defined, everything that happens follows from them naturally. Such a system doesn't require intention. It doesn't require a thinker. A thought doesn't depend on a mind. It depends on structure, on a pattern that evolves according to its own logic. This brings the idea into focus. When we examine how galaxies move, how particles interact, how atoms bond, how light propagates, every behavior seems to arise from principles that sit deeper than matter itself. Not simply forces acting on objects, but rules that define how objects can exist and interact at all. This doesn't eliminate mystery. It clarifies where the mystery lies. If the universe is fundamentally a structure, then that structure is something we occupy from the inside, something we participate in. Our ability to write equations, build models, and make accurate predictions is evidence that we are part of this system, not observers standing outside it. The logic of the universe includes us. You don't need to fully accept that the universe is a mathematical or informational structure, but as a working possibility, it changes how some questions look. If the universe defines its own framework, then it may not require an outside. It may not need a boundary. It could be complete because its rules are complete, not because it contains everything in a spatial sense. And this circles back to our recurring fixation on edges. Even after hearing that the universe might not have an outer boundary, the instinct to imagine one persists. We still imagine a final galaxy, a final photon, a final frontier, because our thinking is shaped by limited environments. Rooms have walls, maps have borders, time in daily life has clear markers. Our lives operate within distinct ranges, and our attention focuses on finite segments. So, even though physics describes space as potentially unbounded, our minds tend to look for limits. It's a habit rooted in local experience. Boundaries help us classify, organize, and interpret the world. They tell us where one thing stops and another begins. But when we enlarge the scale to the size of the universe, that framework becomes unreliable. Space shows no sign of a physical border. Time shows no externally imposed endpoint. The equations that describe the largest structures don't terminate at the edge of the last star. They continue without requiring a stopping condition. These models continue without stopping. They extend as far as the mathematics allows, and nothing in the equations requires a final boundary. That's difficult to internalize, not because the scale is large, but because it doesn't resemble the kinds of systems we interact with daily. Tables end. Books have last pages. Sentences conclude. Our environments reinforce the idea that everything should have a limit, a point where it stops or transitions into something else. It's natural to assume that the universe follows the same pattern, that somewhere there should be a final point. But the more we investigate, the less that expectation fits the evidence. Still, we return to the idea of an edge. Not because the science is unclear, but because of how human cognition works. We instinctively divide and categorize. We separate inside from outside, known from unknown structure, from background. Those distinctions are necessary. They help us interpret the world. But the same cognitive habits make certain cosmological conclusions harder to accept. When scientists say that space might be infinite, it isn't meant as a metaphor. It's a literal possibility based on current measurements. The geometry may not curve back on itself. The topology may not close. The extent may not terminate. Yet, when we hear that the intuition persists, we still search for the boundary, still imagine what might lie beyond the final galaxy or the last cluster. That reaction isn't skepticism, it's simply the residue of the framework we think within. We continue holding on to the concept of an edge, even when the physical universe may not provide one. This inclination appears in other questions as well. We ask what came before the Big Bang, even when the models imply that time itself began with that early state. We ask what lies outside the universe, even when outside ceases to be meaningful without space to contain it. These questions aren't mistaken. They're part of the natural process of inquiry. Every observer begins from a specific position with specific tools. Measurements require coordinates, clocks, detectors, each of which imposes a frame. Our questions arise from that internal perspective. That's why certain puzzles persist. It isn't that the answers are absent, it's that the questions inherit assumptions from our limited point of view. We expect boundaries, origins, and external contexts because those concepts structure everyday experience. There's value in recognizing that. It doesn't require discarding the questions, but it allows us to see the assumptions embedded within them. When we ask, "How big is the universe?" we often expect a finite answer. When we ask, "What's beyond it?" we expect a location. When we ask, "When did time begin?" we expect a moment preceding another. These expectations aren't errors, they're reflections of how we navigate the world. But the universe, as described by modern cosmology, may not conform to those categories. Recognizing the difference helps clarify what we're really asking and what the scientific models are actually describing. Even after everything we've explored, it's clear that no single answer brings the search to a stop. Understanding the universe isn't about reaching a final conclusion. It's about recognizing how each question fits inside a much larger structure, one that continues whether or not we're examining it. And for now, it continues quietly. Wherever you are at this moment, you're within that structure. You're surrounded by space that has no confirmed edge, guided by time that moves forward through conditions we still work to understand. You don't need to solve the universe to be part of it. You already are. The unbounded nature of reality isn't distant or abstract. It appears in the continuity of time, in the way distances can always be subdivided in every measurement that extends into finer and finer detail. If your thoughts begin to slow or your attention drifts, none of this changes. The expansion of space continues at its own pace. Galaxies evolve. Light moves outward. The underlying rules carry on. The open questions remain open, waiting for whenever you return to them. And if you rest, if your eyes grow heavy or your breathing settles, you're not stepping away from the universe. You're simply pausing your place within the ongoing story it tells. The cosmos doesn't require you to hold it in mind for it to continue unfolding. It has been evolving for billions of years before you, and it will for billions of years after. When you wake, or when curiosity brings you back, the questions will still be there, not at the boundary of anything, but at the center of your own capacity to ask. And whenever you're ready, we can pick up the path again.